Now, today in this session, we are going to see the proof of Gauss divergence theorems and few more different laws in electromagnetic theory. Now, we go with the Gauss divergence theorem. Gauss divergence theorem states that the surface integral of a normal flux density over any closed surface in an electric field is equal to the volume integral of a divergence of the flux enclosed by the surface. That means integral of d dot ds is equal to volume integral of del dot d dv. This is the Gauss divergence theorem, which states that the surface integral of a normal flux density over a closed surface in an electric field is equal to volume integral of divergence of a flux enclosed by the surface. Now let us see how this theorem can be proved. Now look at the diagram. Consider a Gaussian surface S enclosing a volume V. Let the charge dq is enclosed in a small volume dv inside the Gaussian surface. If rho is a charge density inside the volume, then the charge density is given by rho is equal to dq by dv. That means let us see that if a charge q is enclosed on this surface, and consider a small element of dv, volume element dv, having a charge of dq in that volume element dv. If rho is a charge density, density is equal to charge per unit volume. So charge density is dq by dv is equal to density, charge density rho. Taking the value of dq, cross multiplying rho dv gives you the amount of charge enclosed in a small volume element of dv. So it is dq is equal to rho dv. Then the total charge enclosed by the Gaussian surface is given by capital Q. Capital Q is the charge enclosed over the closed surface. So capital Q is equal to integral of dq. That is integral of rho dv, because we came to know that dq is equal to rho dv. Substituting that value rho dv here, we know that rho is equal to del dot d. According to the Maxwell's first equation, rho is equal to del dot d, or divergence of d is equal to rho. So from here we know that capital Q is equal to charge enclosed, total charge enclosed by the Gaussian surface Q is equal to integral of del dot d dv. Substituting the value of that value of rho into the above equation, Q is equal to integral of rho dv, we are getting the equation 1. According to the Gauss law of statistics, total charge enclosed capital Q is equal to surface integral of d dot ds over a closed surface. So according to the law of electrostatics, we know that capital Q, charge enclosed, is equal to surface integral of d dot ds. So from equation 1 and 2, we can equate, since LHS are equal, RHS can be made equal. Therefore, integral of d dot ds is equal to integral of del dot d dv. That means this Gauss law of Gauss divergence theorem relates between the surface integral and the volume integral. This is the Gauss divergence theorem which relates the surface integral with the volume integral. Next is the Stokes theorem. Here in our syllabus we do not have the proof of the Stokes theorem, but you have to know what exactly the Stokes theorem gives. Stokes theorem states the surface integral of a curl of f over any surface bounded by a closed path is equal to line integral of f around that path. That means the Stokes theorem gives the relation between the surface integral and the line integral. That is integral of del cross f ds is equal to integral of f dot dl. That means it is giving the relation between the surface integral and the line integral. So if you consider the curl of f, if it is given in the diagram, if the curl of f over a surface bounded by a closed path is equal to line integral of f around that path. Next is Gauss flux theorem in magnetism. Consider a closed Gaussian surface magnet S. Magnetic lines exist in the closed surface. For a closed surface in a magnetic field, the total inward magnetic flux into a Gaussian surface is equal to the total outward flux. That is, the net flux flowing through the Gaussian surface is 0 and is given by integral of b dot ds equals to 0. What exactly this says is Gauss law theorem, flux theorem in magnetism is, if you consider a Gaussian surface, yes, the magnetic lines exist in loops. We know that it starts from north pole and ends at the south pole. It will be in the loops. So for any closed surface in a magnetic field, the total inward flux into the Gaussian surface is equal to the outward flux. That means the net flux through the Gaussian surface is 0. Therefore, integral of B dot ds is equal to 0. It is over a closed surface. From Gauss divergence theorem, we know that integral of B dot ds over a closed surface is equal to volume integral of del dot B dV. Since B dot ds is equal to 0, for volume integral also goes to 0. That implies del dot B equals to 0, which is another Maxwell's equation. So these are the two Maxwell's equations which we have seen till now. Next we see the Ampere's law. Ampere's law states that the circulation of magnetic field strength H along a closed path is equal to the net current enclosed by the surface. What does Ampere's law states is? Ampere's law states the circulation of the magnetic field strength H along a closed path is equal to the net current enclosed by the surface. So integral of H dot dl is equal to I. This is the Ampere's law. By applying Stokes law, we get integral of del cross H ds is equal to integral of H dot dl, because Stokes law gives the relation between the surface integral and the line integral. So from 1 and 2, the equation for I can be written as I is equal to integral of J dot ds, because charge density is current per unit area. So we rearranging the term, I is equal to integral of J dot ds over a closed surface. So from 1, 2 and 3 we can say that surface integral of del cross H ds is equal to surface integral of J dot ds from equation 2 and 3. Thus we get the Ampere's law as del cross H is equal to J. J is the current density and H is the magnetic field strength. But Maxwell modified this Ampere circular law to suit the time varying field and given by del cross H is equal to J plus d dou d by dou t, where d is the displacement current. This equation is called as a Maxwell's Ampere's law, because Maxwell has modified the Ampere's law and he has given the del cross H is equal to J plus dou d by dou t. This is called as a Maxwell's Ampere's law, which is a Maxwell's equation. Now next we see the Faraday's laws of electromagnetic induction. We have seen in our lower classes Faraday's laws of electromagnetic induction. First law states that whenever the magnetic flux linked with the closed circuit or a conductor changes, an EMF is induced in it. That means whenever there is a magnetic flux linked with the coil changes, an induced EMF is being developed in the closed circuit or a closed conductor. This is the first law. Second law states that the magnitude of the EMF induced is directly proportional to the rate of change of magnetic flux linked with the loop. That means induced EMF is directly proportional to the rate of change of magnetic flux. Rate means d phi by dt. Phi is nothing but the magnetic flux. Rate of change of magnetic flux means d phi by dt. So induced EMF E is equal to minus d phi by dt. Here the negative sign indicates the induced EMF opposes the flux change. If there are n turns in a coil, then induced EMF E can be written as minus n into d phi by dt. Here the negative sign indicates the direction of induced EMF opposes the flux change. Next, Faraday's law in differential form is del cross E is equal to minus dou B by dou T, which is the Maxwell's equation. So from this Maxwell's equation, we can reduce the differential form as del cross E is equal to minus dou B by dou T, which is a Maxwell's equation. So we have seen in all these laws, we have seen 4 Maxwell's equation. First is Maxwell's Gauss law, that is del dot D is equal to rho. It is density, which is called as a Gauss law. So these 4 are called as a Maxwell's equations, which led to the revolution and could explain the most of the electromagnetic fields and magnetic laws also been explained using the Maxwell's equation. Del dot D is equal to rho is called as a Gauss law. Del cross E is equal to minus dou B by dou T. It is because of the Faraday's differential law, Faraday's law in differential form. Next is del dot B equals to 0, Gauss law for magnetic field. That means rate of flow of magnetic field into the is the same as a net flow out. So it is called as a Gauss law for magnetic field del dot B equals to 0. Lastly, we have seen that Ampere's law is modified by Maxwell, and it is nothing but del cross H is equal to J plus dou D by dou T, which is nothing but a Ampere's law. So these four equations are called as Maxwell's equations and very important for explaining any electromagnetic theory or any laws in the physics. Thank you.